Alright, here we are. We're going to start talking about Newton's laws. This is 5.2. Our objectives are state Newton's first law and explain its meaning, calculate the effect of forces on objects using the law of inertia, explain conceptually why moving objects do not always appear to be obeying the first law. Okay, assessment. According to the first law, an object at rest will what? Accelerate inversely proportional to its mass, remains at rest because it has zero acceleration, remains at rest unless acted on by a net force, remains at rest due to the constant presence of friction. According to the first law, an object in motion remains in motion forever at the same speed, with acceleration inversely proportional to its mass, at the same speed and direction unless acted upon by a net force. At the instance shown, an object is moving upward with a speed of 25 meters per second. There are constant forces acting on it shown on the free body diagram. Predict the behavior of the object. A puck slides across an ice rink. The weight and normal force on the puck cancel out, but the puck gradually slows to a stop. Why doesn't the puck obey the first law, staying in motion at a constant velocity forever? Our physics terms are going to be at rest, inertia, inertial reference time. Alright, the first law. The first law has two parts. The first is obvious from experience. An object at rest remains at rest. So this is the first part of the law. The second part goes an object in motion remains in motion with the same velocity. This is the important part. So an object at rest will remain at rest. Give an example of the first part of the law. So book sitting down, a chair sitting there, a man sitting on a chair, all of these have zero force. The net force is zero. Net force is zero. When your net force is zero, that means you have zero acceleration. That's a key point. Zero acceleration, zero net force. Zero net force, zero acceleration. And the second part, an object in motion remains in motion with the same velocity. In real life, all moving objects eventually slow down and stop unless you continually apply a force to keep them going. It will slow down eventually unless you apply a force to keep it moving. That's important. Well, then, is the first law wrong? Well, this is kind of cut off, but is the first law wrong? No, it's not. Why is it not? Why is it not wrong? Because as it's rolling, what is it rolling on? What is this surface doing to the ball? That surface is going to have friction, and that friction is applying a force in the opposite direction. So it's slowing the ball down. So to keep it moving, you have to apply another force to it to keep it rolling to overcome friction. Alright, with Newton's first law, when the net force is zero, net force means total force, all the forces acting on it. So net is the key here. All the forces acting on it are zero. And this would be called your blank screen. Continuing on. What are all the forces on the ball? And this has kind of got cut off. I'm really sad that this got cut off. What are the forces acting on this ball? Well, if you look on it, the weight of the ball is going to get pushed down. So if you have the ball going down, that's your weight. FW, weight. Remember, that was mass times gravity. Again, it's another blank screen. Another blank screen. But I'm going to draw what I think that they're trying to give you. With the ball, you have a force going down, which is the weight. What's going up is called the normal force, going that way. If the ball is rolling this direction, the opposite direction is the force of friction. And the force that goes this way is what we call the applied force. And basically this is a force diagram, what they're trying to say. So the weight goes down, the normal force goes up. The normal force basically cancels out the weight because it's going to be the same force going upwards. Because if you look at a ball on a table as it rolls, it's not going down and it's not going up. Well, we know the weight is pulling down, while the table's pushing back up on it with the same amount. You're applying a force this way, but there's a frictional force that slows it down the other way. That's why a ball will slow down whenever it's rolled. And yet another blank one. You guessed it, another blank one. So it looks like there's a lot of blank slides in here that got copied over, and I'm just going to talk through them because I can. Again, we're happy. Yes, another one, blank one, and now we're not so happy. Yes, we have even more not being happy, or maybe we are. There's my attempt. Here's a chin. For your pleasure, here is an airplane. And it's smiling. I'm really hoping we're coming to the end of these. All right, now back at the notes. So what I wanted you to get from those last ones was the free body diagram that I drew on the one. All four forces that were acting on it. As they cancel out, it makes it zero. If there is zero net force, then you have no acceleration, you have no net force, you have Newton's first law. So, looking deeper, consider sitting in your chair. Are you at rest right now? Sitting in your chair as you're listening to this, are you at rest? Yes, you have zero net force. So you're an object at rest, you will remain at rest. Some of this will depend on your frame of reference, because the further away you are, you're going to take a different frame of reference. Earth's orbital velocity is 29,780 meters per second. Imagine you are in a sealed box moving with constant velocity. You cannot look or sense outside the box in any way. So you're inside the box, sealed in, and you don't know what's going on. No physical experiment you can do within the box can distinguish whether you're moving or at rest. Because if you're in the box, that is your whole world. There is nothing outside of the box to you. In physics, being at rest or moving within a constant velocity are equivalent. They are both cases of unaccelerated motion. They are both examples of Newton's first law. So, understanding the first law, when the net force is zero, an object at rest will remain at rest, and it's got to have both, an object in motion remains in motion with the same speed. These two parts work, so the net force is equal to zero, then the acceleration equals zero. This might be the most important part of all of this for you to remember. And we're going to talk more about this in class, about net forces and accelerations and stuff like that, when we get back on next week. So, the first law goes both ways. If the net force is equal to zero, then you know acceleration is zero, or if acceleration is zero, then you know the net force is zero. They both go together. Motion only changes through the action of a net force. If the net force is zero, there can be no change in motion. None. The law of inertia. Newton's first law is also known as the law of inertia. Inertia is the tendency of an object to resist change in the speed or direction of its motion. The inertia of an object is related to its mass. The more massive an object is, the more inertia it has, and the more it will resist having its motion changed. This is the first law. All right, here's your assessment question. According to the first law, an object at rest accelerates inversely proportional to its mass, remains at rest because it has zero acceleration, remains at rest unless acted upon by a net force, remains at rest due to the constant presence of friction. Remains at rest unless acted upon by a net force. You have to have a net force act on you to move you if you are at rest. According to the first law, an object in motion remains in motion forever at the same speed, with acceleration inversely proportional to its mass at the same speed and direction unless acted upon by a net force. at the same speed and direction unless acted upon by a net force. You see a little pattern here with net force. At the instant showed, an object is moving upward with a speed of 25 meters per second. There are constant forces acting on it, shown on the free body diagram. Predict the behavior of the object. So if you've got 30 going this way and 30 going that way, what happens to them? They're canceling out. If I've got 10 going this way and I've got 10 going this way, what are they doing? They're canceling out. So if everything cancels out and it's moving upward at 25 meters per second, the object will move upward at a constant 25 meters per second as long as these are the forces acting on it. All the forces canceled each other out, so it kept doing what it was doing. A puck slides across an ice rink. The weight and the normal force on the puck cancel out, but the puck gradually slows to a stop. Why doesn't the puck obey the first law, staying in motion at constant velocity forever? The net force on the puck is not zero. There is a small amount of friction that causes the puck to slow down. Remember, we had the weight going down, and we said the normal force going up. It's like this. Remember, this says up here the weight and the normal force cancel out. So these are canceling out. Well, the puck was probably sliding this direction, but that way we have friction, and that friction is what slows down the puck. Okay, that's the end of the chapter. This was only Newton's first law. He has a second law and a third law that you need to know, and they're in the textbook. You need to know the second and third law also, and we'll talk about those in class.